dissociation equations and just talk about what happens when salt separates into ions in a solution and how that affects concentrations, and then look at some practical examples of things we might want to be able to do with this information. Okay, so for each question we're going to assume the solute dissolves completely. That's our first idea. I think actually I'd forgotten I'd written that and added that statement to a lot of these questions. All right, and we're also going to list the dissociation reaction. All right. So we're going to, number one actually is solved for us, but I'm just going to go through it just to make sure that we understand the logic behind the answer. All right. So we're asked, what is the concentration of each ion? What is the concentration of each ion in a 10.5 molar sodium sulfite solution? Okay. So what does that mean? That means we have some solution, right? And it has some sodium sulfite in it. So it's mostly water, but it has about 10.5 M stands for moles per liter of something, sodium sulfite. Sodium sulfite has is a compound, and it's an ionic compound because it's a metal, sodium. And I know sodium is a metal because it's on my periodic table in the metals area, so that's a sodium there. So we're going to have some sodium, some Na, and that's going to have a charge. Now, if I want to know the charge, I could know, for instance, that all my species in this left column, are, except for hydrogen, are alkali metals. And all of them have a charge of +1. All these guys, incidentally, have a charge of +2. And then we get into the weird area of transition metals where there's all sorts of weird rules. So maybe I know that as a pattern. Maybe I don't. If I don't, I might look on my table of polyatomic ions, table of common ions. And I'd look for sodium alphabetically. In the S section, I'd say, oh, sodium has a charge of +1. So there's two ways we can know that. Okay, so that means I have a sodium, and so that means one of my ions is sodium plus. And then we have sodium sulfite. So I might look again and see, oh, one of my common ions here is sulfite. Yeah, okay. And sulfite is SO3 2-. So another ion is SO4 3-. And maybe I should make that writing a little bigger so we can see that on the screen. 3-. Okay, I'll try to write a little bigger. And wait, did I say that right? 3-, 2-. Gosh. All right. So, okay, and what I know is that in an ionic compound, the number of positive charges and negative charges have to be equal to each other. So what that tells me is that I need at least another positive charge from the sodium to balance it. So now I have 2 sodium, so 2 plus charges, and 1 sulfite. Sulfite has 3 oxygens. Geez, I really messed up writing out sulfite. Okay. And so, pardon me, so I have 2 positive charges for my sodium and 2 negative charges for my sulfite. So that means it's a 2-to-1 ratio inside that compound. All right. So I put a little 2 subscript here to indicate that's my sodium sulfite. All right, and so I might draw that in here in this solution. I might indicate that there's some sodium ions floating around. And for every 2 sodiums, there's 1 sulfite ion. Now, I could draw more if I wanted, but I think I'm going to keep just 2 sodiums and 1 sulfite just to help me remember that that's the ratio of how many sodiums there are for every sulfite. And I could draw waters in there if I wanted as well. Okay. Now, it doesn't tell me how much I have, so the volume is unknown. But it turns out it doesn't really matter. I don't need to know the volume, how much stuff there is, to know that if I have this concentration of sodium sulfite, then I can make a conclusion, if all of our solute dissolves completely, about how many sodium ions must be floating around, and how many sulfite ions are floating around. Okay. To do that, I need to list a dissociation equation, so that's what I'm going to do next. So I've got an Na2SO3, and I can imagine that being a salt, some probably white powdered substance. And S stands for solid, not salt. And when put in water, that's going to separate into these component ions. I'm going to have some sodium ions that are now aqueous. That's what it means when they're floating around in water like that. They're aqueous. And some sulfite ions, which again are aqueous. And lastly, I need to balance this reaction. So that means that there would be 2 sodiums here, and to balance the Na2 here. Great. Okay. Now, and then we see in the solution, actually, we're given this dissociation equation. Great. All right. And then we say, okay, well, if I have 10.5 moles of this stuff for every liter, the ratio is I have 1 sodium sulfate ion, which creates 1 sulfite ion. I describe this as an ion, it's a compound. So for every 1 of these guys, it makes 1 sulfite and 2 sodiums. The molar ratio is 1 to 2 to 1. Okay, so that means if this solution is 10.5 moles of Na2SO3 sodium sulfite for 1 liter, I can multiply that, and I can see that actually I get, I'll start with sodium, 2 moles of sodium ions for every 1 mole of Na2SO3. And then I see these get moles of sodium sulfite cancel out diagonally. And so I multiply across, I get 11.0 moles Na plus over, it looks like my liters didn't cancel, so I have 1 liter on the bottom, which I could abbreviate as saying 11.0 molar Na plus. Okay. And I can make the same argument for sulfite. I could also say that if it's 1-to-1, I have the same concentration, or I can actually, if I'm more comfortable writing a conversion, I can do that. And now the difference is that it's 1 mole of this stuff down here for every 1 mole of sulfite. And so that I multiply by 1, okay, so that all I've really done is change the units. Now I have moles of sulfite. And the liters didn't cancel, so I'm still over 1 liter, which says 10.5. Oh, wait. 10.5 times 2 is 21.0. 21.0. And molar sulfite. Okay. And those are our 2 answers, which were given, of course. All right. That's not very clear, so that's 21.0 molar Na plus. Great. All right. So let's move on. So this question says, again, what is the concentration of each ion? What's the concentration of each ion in a solution that's formed when 94.5 grams of nickel sulfate is dissolved in 850.0 milliliters of water. Okay. So, to answer that, okay, so I might list some things I know. I have 94.5 grams of nickel 3. That means, okay, so my ions are nickel, write that a little bigger, nickel 3 plus. That's what that nickel 3 means. It means nickel with a positive 3 valence is the word we give it. Sulfate, well, sulfate is on my ion table as SO4 2 minus. SO4 2 minus. All right, and so I know that, and so I'm going to write my compound here eventually once I figure out what the ratio of each of these will be to balance the charge. But I also am going to list that I have a volume of 850.0 mils. That's water. Maybe it's relevant as water, maybe it's not. And this is a mass. Okay. So we'll see what we can do here. First of all, we have to balance these. Now, they're not neutral right now. There's too much positive charge, so I might need another sulfate ion. But now I have three positive charges and 4 negative charges. So that's overall negative, so I needed some more positivity. I'm still not balanced, so now I have positive 6 for my nickel and negative 4 for my sulfates. So I'm going to add another sulfate to give us negative 6. And so then overall, we get 6 positive charges and 6 negative charges, and that is neutral. That tells me that I'm going to have some nickel 2, SO4, 3. Okay, and I know some volume. Okay, and I can draw a picture of what's happening here. So here I'm adding some nickel sulfate, and so I end up with 2 nickels floating around for every 3 sulfates. And these sulfates, the oxygens and the sulfurs, these are nonmetals, so they're bound together with covalent bonds. So water is not enough to break these guys apart. They will not dissociate. They're going to stay together as a polyatomic ion. All right. So, okay, so it looks like we have this dissociation reaction, which says that we have some nickel 2 sulfate, nickel 3 sulfate, and that's a solid, and that's going to dissociate into, I'm going to have 2 nickels, and they're aqueous, floating around in water. And in addition, I'm going to have 1, 2, 3 sulfates, and those are aqueous as well. Okay, and that's our dissociation reaction. Now, what are we asked for again? We're asked for the concentration. What's the concentration of nickel 2 plus? What's the concentration of sulfur? Oh, 2 plus? 3 plus. I don't know where I got 2 from. 3. I do know where I got 2 from. I got it from the fact that there's a 2 for a subscript in here. All right. So concentration. So that means really what I'm looking for is some number of moles of Ni3+ over some number of liters. And I also need some number of moles, SO4, divided by some number of liters. And that will give us a concentration, or molarity, right? Okay. So I know know the volume. I know how many liters I have. I have 850 milliliters, or 0.850 liters. So that's fine. But I don't know the number of moles of sulfate or the number of moles of nickel. Okay. But what I do know something, though. I know that I have a mass, and I know if I have a mass of a substance, I can find the number of moles using molar mass. So I'm going to start with my 94.5 grams of nickel 2 sulfate. Okay. And I can convert this into a number of moles of nickel 3 sulfate. I think I said nickel 2 because of the subscript. I'll probably do it again. So I apologize for that. So what is the molar mass of nickel 2 sulfate? Well, I know nickel 2 sulfate has 2 nickels, and it has 3 sulfurs and 12 oxygens. So the mass of 2 nickel atoms is 58.7 grams per mole. So there's 2 of them. So 2 times 58.7 is 117.4 grams per mole. I have 3 sulfurs, so that's 3 times, what's the molar mass of sulfur? 32.1. 96.3 grams per mole. And I have 12 oxygens, which is 12 times 16, a little glare there, 192 grams per mole. So that means the molar mass is 192 plus 6.3 plus 117.4, 405.7 grams per mole. Actually, that's a case where I'm adding sig fig, so I would retain 4 significant figures here. All right, so that tells me that a mole of this stuff weighs about 405 grams. A little bit more, 406 grams-ish. So I only have 94 grams, which means I probably only have about a quarter of a mole or so. I don't quite have that much. I have a little less than a quarter, I would say. Let's find out exactly how much. So I want my grams of nickel 2 SO4 3, that's a mouthful, to cancel out diagonally. So I'm going to put the mass down on the bottom, 405.7 grams of nickel 3 sulfate. And that's for every 1 mole. And here I've converted, into, I didn't really leave enough room, even though I had tons of room up here. That's frustrating. So that's going to be, I'll just try and squeeze it in here, nickel 2 SO4 3. And those are moles now of the nickel 2 sulfate. That's how many moles of nickel 2 sulfate were in here. However, that's not an answer to the question of how many moles of nickel we have. Nickel ions. To do that, we need to convert these moles of nickel 2 sulfate and into moles of nickel 3 ions. And I can see in my molar ratio that 1 mole of nickel 3 sulfate makes 2 moles of nickel 3 when dissolved in water. I can see that here. There's 2 of them, and I can imagine all of those would make 1 nickel 2 sulfate compound. I'll leave for now the fact that these exist in really an array rather than individual molecules like they do with covalent compounds. So we're going to skip over that for now. All right, so it tells me that I have a ratio of 2 nickel 3s, 2 moles of nickel 3 for every 1 mole of nickel 3 sulfate. Okay, and that'll give us the concentration. Pardon me, not the concentration, just the number of moles of nickel 3, because I can see moles of nickel 3 sulfate cancel out and grams of nickel 3 sulfate cancel out. So that tells me that I end up with 94.5 times 2 divided by 405.7, which is 0.466. 0.466 moles of nickel 3 plus. I can do the same thing here with moles of sulfate. Again, it's actually a very similar calculation. It's identical, really. So I still can convert into moles of nickel 3, pardon me, to SO43 for every 407.5.7 grams nickel 2 SO43. And that's going to convert into, now I have a 1:3 ratio. So 1 mole of nickel 3, oops, it's hard to write 2 and say 3 at the same time. Kind of confusing for me, actually. Over 3 moles of sulfate. All right, and then we see some grams of nickel 3 sulfate canceling out, moles of nickel 3 sulfate canceling out, and we end up with moles of sulfate. So whatever 94.5 times 3 divided by 405.7 is, and it's 0.699 moles sulfate. All right. Now, we were not asked for the number of moles of nickel 3 or sulfate. We were asked for the concentration. How many moles would there be if it was in a liter? So we found out how many moles there are in almost a liter, like not quite. So I would expect the concentration in moles per liter to be a little bigger. We would need a little bit more nickel 3 sulfate to make a whole liter of this stuff if we wanted to keep the concentration the same. All right, so to do that, to find concentration, I have to divide how many moles I have by the number of liters I have. So as a final step, I would say, well, the concentration of nickel 3, can't really read that from the camera, concentration of nickel 3 plus is 0.466 moles nickel 3 plus over 0.8500 liters. And that is 0.466 divided by 850. I don't know why I put that 0 in there. The calculator doesn't know it's there. All right, that gives us 0.548 molar nickel 3 plus. That's one of our answers. And I can do the same thing for sulfate. The concentration of sulfate is 0.699 moles sulfate over 0.850 liters. 0.699 divided by 0.850 is 0.822 molar SO42 minus. Okay, oops. All right, so that tells us that the concentration of nickel ions is about 548 thousandths of a mole for every liter. And there's about 0.699 moles of sulfate if there is a liter. That's the concentration. That doesn't tell us how many there actually are in this vessel, because we don't have a liter, but it tells us if we had a liter, that's how many moles we would have. Okay. So let's move on. Let's take a look at question 3. Purple is a little dark. Let's see if we can do something lighter. All right, question 3 says, okay, if 3.78 liters of some calcium fluoride solution, and so I have 0.378 liters of some concentration of calcium fluoride. And that's added to 6.36 liters of water. So we have a solution, and we're adding more water to it. And it looks like that. The highlighter is Rich's last days. Start the garbage before anybody uses it. 2 points. All right, and lastly, we have a question, so we need to make sure we're going to answer that. And it says, what is the concentration of each ion? Okay, so we have a metal and a non-metal, calcium and fluoride. All right, where to start? Well, what is calcium? Well, calcium's a metal, obviously. Maybe not obviously. We don't always think of calcium as metal, but it actually happens to be. And calcium in its metal form is actually a soft gray metal that you can cut with a knife, I think. I think you can. I actually haven't done that myself. And it's pretty reactive. Now the calcium we think about when we think about calcium in milk, that's in its ion form. So when we see calcium floating around in a solution, it's going to be in an ion form. It's going to be aqueous. And so we'll look in the ion table for calcium. Oh, and it actually forms a positive 2 charge. And that is Ca2 plus is the formula. And then we have this fluoride. And that has a charge, while we're here, of -1. So that tells me that calcium fluoride, I need 2 fluorides to make 1 calcium, and so I get calcium F with 2 fluorides. And that's a solid, and that would dissociate into 1 calcium ion, which would be in an aqueous form, and 2 fluorides. Okay. And, okay, so that's getting us started here. Now I might take a second to draw a picture. So I know I have some beaker, and it's a big beaker, I guess. It's like a bucket. We've got about 3.78 liters, which is roughly like a gallon, like a big ice cream tub. And that's water mostly. And it's got some calciums and some fluorides. Okay. And that has a concentration of 0.960 moles of calcium fluoride for every 1 liter of solution. And that's what 0.960 m means. Okay. Now, we're taking that and we're adding water. So we're going to increase the volume. So what's important is we're not changing the number of moles of calcium fluoride. We're going to change the concentration of it, change how many moles there would be for a liter. But now we're going to have whatever 3.78 plus 6.36 is. So 3.78 plus 6.36. It's going to be a new volume of 10.14 liters, which is a lot. It's like definitely bucket territory we're talking about here. All right. Now what's not changing, we're not adding anything except water. So we're going to be adding water, 6.36 liters of H2O. And when we come over here, we end up with the same number of ions that we had before. And the only difference is how spread out they are, because now there's more water separating them. So we're going to expect the concentration here to decrease over time as we add more volume. So this is what we call a dilution. Okay. So what do we ask? We're asked for what is the concentration of calcium and what is the concentration of fluoride, right? That's what it says when it says what is the concentration of each ion. Resulting, meaning in the new solution, the concentration of each ion, that means the number of moles of fluoride over number of liters, which is 10.14 liters. And it'll be the moles of calcium over number of liters. Okay. All right. So I actually know the number of liters. So again, kind of like the last question, all I really need to do is find the number of moles of my species. And what is important is that is not changing. The number of moles is conserved. So of the original substance, the calcium ions and the fluoride ions are conserved. All we're doing is adding water. We're not changing anything fundamental about those ions, and how, or their frequency at least. Okay, so if I can find the number of moles of calcium here, I know how many moles are in our new solution. So what do I know? I know how many moles would be in a liter. I know how many liters I have, almost 4. So I probably need almost 4 times as many moles of calcium. Oh, that's of calcium fluoride. So what I'm going to do is I'm going to say, well, if I had 3.78 liters of solution, that contains 0.960 moles CaF2 for every 1 liter of solution. Now, liters have canceled. Now I have units of moles of calcium fluoride. But I didn't quite want moles of calcium fluoride. I want moles of calcium. So I'm going to say, okay, well, if I look in my dissociation reaction, I can see that I have 1 mole of calcium fluoride. That converts into, it's a 1-to-1 ratio. Every mole of calcium fluoride gives me 1 mole of calcium ions. Okay. And so to find the number of moles of calcium, I just have to multiply across. I get 3.78 times 0.96 and times 1 divided by 1. So I end up with 3.63 moles of calcium ions. Now, if I want to find the concentration of calcium, that's going to be 3.63 moles calcium over my 10.14 liters. So I'm going to find out how many there would be for a liter. And that would tell me that there's actually only 0.358 moles for every liter of calcium ions. All right, so we can do the same thing for fluoride, and then I think we'll be done. It's going to be a similar process. We've already mapped out what needs to be done. We started with 3.78 liters. Then we have 0.9, so it's still the same thing, really. Moles CaF2 over a liter. Now the difference is it's a ratio of 2 fluorides for every 1 mole of calcium fluoride. So 1 mole of calcium fluoride makes 2 moles of fluoride ions. And so that gives us a value slightly, well, twice as large as the last one. So I could actually just take that number and double it, but I'm just going to go through the steps from first principles. 3.78 times 0.96 times 2, and that's like 7 1/4. And then I need to find the concentration of fluoride, which is 7.26 moles. Fluoride over 10.14 liters. That's going to be equal to, divided by 10.14, 0.716 molar of fluoride solution. Okay. All right. So what we've done here is we've done 1, 2, 3 sort of flavors of question. And if we read through, we may be able to find now that a lot of the questions here match up. They're very similar in some way to other earlier iterations of these questions. So I'm going to leave some of these. I'm not going to solve all of these in this video. But I am going to jump down and do one of these questions from this new sort of flavor of question. And I'm only going to do question number. Well, let me just read these over again and just make sure they're roughly the same. Molarity is a little easier. The number of grams is a little harder, so I think I'm going to concentrate on number 11 here. Okay, so for the last one, we're going to look at question 11. So, question 11. By the way, I'm starting with question 11 because I think any calculations you need for 9 or 10, you should be able to do using the calculations with question 11. We might actually have to just add another step. All right. So for question 11, okay, we have, so we're told a chloride concentration. And it's in a volume. It's a aluminum chloride solution. Question is, okay, well, how many grams of aluminum chloride are in the solution? This very practical question. It's very common for you to need a certain volume of a solution with a certain concentration, and you got to make it. Happens all the time. And you got to know, well, how many grams do you weigh out on your scale? A kilo? A microgram? Somewhere in between? So what we know is we have some beaker, and we have 100.0 mils, which is the same thing as saying 0.1000 liters. Okay, and we know we have some aluminum ions and some chloride ions. So the chlorides are floating around here. There's probably a 3-to-1 ratio. So I'm going to represent 3 times as many chlorides as aluminums. And they're just floating around in the solution. Okay, and I know the concentration of these guys. Concentration of chloride equals 0.600 moles of chloride ions for every liter of solution. Now, we don't have a liter of solution, we have 1/10 of a liter. So that tells me already we have 1/10 of this number of moles floating around here. And that's going to help us find out how many grams overall of our overall mass we have. Okay. We might write a dissociation reaction. It might be nice and formal. So actually we're given the compound in this question. I think it's so we're a little freer to think about the ins and outs of this question. So it's going to start as a solid, and then it's going to dissociate when you put it in water to turn into aluminum ions that are aqueous, and 3 chloride ions for every one of these you add in. Okay. So, I'm going to see if we can start talking about chloride ions. So we're going to start with some chloride ion talk and somehow get all the way to talking about chloride concentration. We're going to see if we can transfer and talk about aluminum chloride mass. And mass is measured in grams. So somehow we have to get from talking about a concentration of this in a volume certain volume that's given and turn it into a mass. Okay. So to do that, the most local value we have here is this fact that we have 100 mils, or 0.1000 liters of solution. And in that tells me I have 0.600 moles of chloride for every 1 liter. Now, that now tells me about how many moles of chloride ions I have. And I can now make a conclusion about how many moles of aluminum chloride I must have mixed in. So for every 3 moles of chloride, 3 moles, I have 1 mole of aluminum chloride. That's looking pretty good. So we're not at mass of aluminum chloride, but at least we're now in moles of aluminum chloride, and I know how to convert between moles and mass. I'm going to use the molar mass of aluminum chloride. So to find the molar mass of aluminum chloride, I actually like to just look up my molar masses on my mass chart because it's alphabetical, but it's also, I would say, a very good habit to be able to locate aluminum and chlorine on the periodic table. So if you aren't comfortable with where aluminum chloride are, it might be a good exercise for you to hunt them down so that you can find them. There we have aluminum and chlorine there. So I've got an aluminum. Here's a mass of 27. Oops, not 0.27, just 27. We're going to add that to 3 chlorides actually, but the extra electron to make it a chloride is negligible in weight, so we'll add 0.35, but we have 3 of these chlorines, so we're going to times it by 3 and get 133.5 grams for every mole. So aluminum chloride is a molar mass of 133.5 grams for every mole. And so if I want to convert the moles of this to grams, I could say 1 mole of AlCl3 is equal to 133.5 grams of AlCl3. And that tells me now the mass we must have had to weigh out. So let's find out. That'll tell us grams of AlCl3. It's going to be 0.1 times 0.6 divided by 3. Just to make sure, I'm going to press equals and times that by 133.5 grams per mole. And that's not much. It's 2.67 grams of aluminum chloride that we have to weigh out in order to make this solution. All right. So if you have any questions about any of these in-between examples here, please let me know. I would say this is a pretty useful skill, pretty practical skill for everyday lab experience. You need to make a solution, very common thing to have to do. All right. Well, good luck studying.